All right, we have another integral from MIT 2022, regular season number 10. And for this one, it's a little more complicated than sometimes what we get when we have this kind of case where we have a constant base. So it's this kind of a to the x situation. I think what we're going to need on this, we're definitely going to need to know how do you integrate something like this, and we'll get that formula, and we want to know how to differentiate that. So we have our formulas over here to the right. This just comes from rewriting a to the x, where a can be 2 or 4 or whatever, and we just rewrite it with e as the base, and then just doing the normal business to differentiate or integrate it, we get this. So before we get started, I think maybe it's nice to clean it up though and do it with the u substitution. I guess you probably could skip it, but let's do the u sub. And because I want to do the u sub for this, just noticing that 4 can be written as 2 squared, so we have 2 squared to the x there. But then with exponent properties, I can switch it around and write this as 2 to the x all squared. So if I do my u sub for that, then we can use it on both these things. We can have u equals 2x, and just to show it, we'll have u squared is going to be this thing, which is the same thing as this. Take a derivative here, du, we use this formula. We're going to get back 2 to the x with an ln2 in front. So now we'll go ahead and substitute and see what happens. Again, our 4 to the x is going to be u squared. This piece becomes 3 to the u, and dx is going to be, sorry, I should have a dx over here. And actually what that means is I should put it back where we can do the substitution. So like solving for dx, this thing is going to be du over ln2, and this thing is just u, so something like that. So then here we have du over a u, and the ln2, that's going to come out as a constant over here like this. But then I can cancel one of these with one of these. And then what we're left with here, we can do with integration by parts. I don't want to erase the formulas, so maybe let me clean up this and we'll see if we can squeeze in a DI table for integration by parts. Okay, now for my integration by parts, we'll differentiate the u, we'll integrate 3 to the u. So coming over here, we'll differentiate this to 1, and then do it one more time, differentiate to 0. Over here, integral, we can use a formula again. I mean, I guess we used this one before, so we use this one, and it's going to be 3 to the u over ln3. And then we do it again. That's just a constant, so what happens is we get 3 to the u over ln3 all squared. Okay, now let's see if we can pull it all together. The last row, that's going to be zeroed out by that 0 there. And we got solution, or part of the solution on the diagonal. Now we're going to have 3 to the u in common. We're going to have ln3. The way I'm going to factor it is, let's do it like 3 to the u. I'm going to take out ln3 squared. I just like doing it this way. You could probably do it a different way. So we'll factor out that, and we still have this ln2 over here. Then let's see what's left. Here we're going to have u, but we need to multiply in another ln3 just because of the way we factored it. And then all that's left here is just a -1. And so now all that's left to finish is we just need to back substitute, but I erased my u sub. If you remember, it was just 2x. This was our u right here. So back substitute to finish it, and what we get for a final solution is going to be 3 to the 2x over ln2, ln3, all squared, 2 to the x, ln3 minus 1, add a plus c, and that's it. Okay, so there you go. Not too different from the normal kind of problems we see when we have a constant base. They just kind of made it a little messier with the integration by parts and putting it in 2 places, but otherwise, just use these formulas and you're good. All right, that's it for today. Thanks everyone for watching. Have a good day.